Hi, hello, good evening, everyone. Am I audible? Good evening. So let us start. So this week we are going to see, uh, the week 9 content, which is based on DAC and ADC circuits and how to solve problems based on that. So I hope you might have gone through the lectures. So let me take a couple of problems to begin with. Okay. So there are a couple of ADC circuits. To start with, we are going to consider a dual slope type voltmeter. Okay, so uh, let us start with a problem. Here, uh, clock is fed, clock of 5 kilohertz is fed to dual slope voltmeter. Okay, and voltmeter has voltmeter integration time. So we will look at each terms, what they mean. First, let me write the problem statement here. So voltmeter integration time is 2000 clock cycles. Okay, and during this voltmeter measurement, we are going to detect some unknown input voltage, and we are going to find out the how much value of the uh, reference voltage is. So reference voltage is given 4 volt, and this integration time is also given, that is 190 clock pulse. Okay, so this is integration, which is 2000 clock cycles with unknown input voltage, which we have to find. And this is the disintegration time of 190 clock cycles with reference voltage of 4 volts. Okay, and we have to find out the input voltage. Okay, so that is our problem. So first, let me go through the basics of dual slope voltmeter. What are they and how do we measure? So basically, the basics of it is, if you have any unknown input voltage, and what it happens, it will have to consider both integration time as well as disintegration time. So let us consider some input voltage. So this will be the slope, right? So Vx into T1. Let us suppose it takes T1 time, which is in our case 2000 clock cycles, right? And disintegration time is, no, we are into T2 minus T1, because this time will be T2. So this whole time will be T2 minus T1. Okay. So here it is the integration. This is the disintegration. So can we equate both the slopes here, right? So how to equate it? Yes. So we can equate it, right? So Vx into T1 is equal to Vr into T2 minus T1. Okay. So that's what we had to do in our question, right? We were given with 5 kilohertz clock frequency with integration time is 2000 clock cycles. If we have in terms of clock cycles, we can equate it with time. 2000 into clock cycles. So clock cycles is nothing but frequency. So frequency is 5 kilohertz. So that much time it is gonna take to measure the or to reach the unknown input voltage. So this much will be how much? 4.4 seconds, I guess. Yeah. Hmm. Yeah. This much will be 0.4 seconds. So let me write Vx, or you could also write in terms of clock cycle because in any way frequency of both the clocks are same or frequency of both the equations are same here and here. So T1 we can write as 2000, right? Vx is the input voltage, unknown input voltage equal to VR. VR is the reference voltage. So reference voltage is how much? From this problem, can you see how much is the reference voltage?
Okay.
4 volt. Nice. So it is 4 volt into how many clock cycles? T2 minus T1 will be corresponding to
I
190. So that
190.
is 190. So that is the disintegration time, right? We do not need to multiply it with time, which is inverse of frequency here also, because both will be cancelled out, right? So that is why we are ignoring them. So here can we easily measure 4 into 190 divided by 2000, which will be how much? 190 into 4 divided by 2000, which is 0.38. So it is 0.38 volt. Okay, so that much of the unknown input voltage we were measuring, right? With reference voltage of 4 volt, we can get so much of input time. So did you get the idea behind this dual slope type voltmeter? Okay, and also you could see that this type of voltmeter or this type of ADC will be slower, right? Because it will have to provide, we have to connect a reference voltage to disintegrate how much the quantity it has been integrated initially. So that is why this ADC circuit is considered as the slowest one, right? Any doubt in this?
No, sir.
Okay, great. Let me see if some more problem related to it can we solve. Yeah, linear type. Okay, so moving towards the second part of this problem, we have to find out the resolution of this voltmeter. How much will be the resolution of this voltmeter? First of all, what is resolution? So let me talk about resolution first a bit. So resolution is the smallest change in input voltage, okay, that can be detected and represented. Yes, lowest possible value that can be measured. Exactly. So if your input can detect the smallest value which will be corresponding to the change in output, so that is considered as resolution. So the higher the resolution, higher will be accuracy and higher will be time consumed by the circuit as well. Okay, so that is what we optimize by reading, various types of ADC like dual slope, successive approximation, ramp type, flash type, right? So those types of ADC we have to choose among them, that depending on the requirement, right? Okay, so as NS mentioned, at lowest possible value that can be measured. So how much the lowest possible value that can be measured in this dual slope voltmeter? Or how to calculate? We will talk about the process, how to calculate it. So the first thing is that we have the reference voltage at 4 volt, okay, and we have the frequency. So in one clock frequency, okay, how much the voltage the meter will read, that would be our minimum voltage. Do you agree? Okay, so we have the reference voltage, we have the clock frequency, and in one clock cycle, how much will be the change or how much will be the change in the step of the voltage level? That would be our answer for this. Do you agree? Yes. Okay. So we have 4 volt and we have to divide it by one clock cycle, which will be equal to 4 divided by 1 by how, how much will be the frequency, right? Clock cycle will be one clock frequency. And how much will be one clock frequency? That is given in the problem itself, that is 5 kilohertz. Okay, so 5 kilohertz divided by, like 5 kilohertz into divided by 2000, so that's one clock cycle. 4 volt it is 4 volt it is disintegrating, equal to 1. 4 volt by clock frequency. Wait a second. 4 volt by clock frequency. 1 divided by 1 by 5 kilohertz. Or we could, rather than this way, we could, just a second, we could rather see in that fashion, because it would be a bit confusing. So we will see in that way that 4 volt is our measure, reference voltage, right? And it is taking 2000 clock pulse to reach that while integrating, right? So in one clock pulse, how much it will detect? Is that right? So 4 into divided by number of clock pulses or clock cycles rather. 4 divided by, so there were 2000 clock cycles required to reach this value. Okay, so 2000, why we are selecting 2000? Why are we not selecting 190? So we had to disintegrate total 4 volt with 190 cycle, but here we are considering 2000. So 0.8 millisecond. Yeah, that we will see how much it is coming out to be. 4 divided by 2, so 2, no, it will be 2 millisecond. Sorry, 2 millivolt per second, because this is in volt, this is in cycles in second. Okay, so that is the answer, but we are more concerned about why we are considering this 2000 cycles, not 190 cycles. Because we have to select the minima of both. Why minima? Because resolution itself, the definition of resolution itself is the lowest possible value that can be measured, right? That you only mentioned. So the lowest possible value, which could be mentioned with 190 cycles, that would be how much? 4 divided by 190. That would be zero point 0.2. So that would be, 21 millivolt per second. Or resolution is generally measured in terms of voltage. You could avoid per second. So the resolution is 21 millivolt. That could be measured with 190 cycles. And with 2000 clock cycles, we are going to have a resolution of 2 millivolt. So the definition itself is the lowest possible value. So lowest possible value can be achieved with the highest number of clock pulses. Right? So that is why we are using here 2000. So is there any doubt? I can repeat this portion.
Repeat, sir, once again.
Yeah. So see, we had to calculate the resolution of this circuit. Okay, we have 2 volt. We have the reference voltage of 4 volt, which is getting disintegrated in 190 clock cycles. Okay, so which means that this disintegration time T2 minus T1 is less than T1. Okay, means this slope would be something like this. Okay, which means a steps here would be also very larger compared to this one. Okay, compared to this integration. Okay, so since steps are larger, this 190 clock pulses, clock cycles rather, clock cycles would not give you the resolution of this circuit. Why? Because resolution is the smallest value which could be detected. And the smallest value could be detected with the help of this clock cycle, 2000 clock cycle. Right? So this voltage value is 4 volt, right? Okay, this 4 volt only getting disintegrated in this much time. But the resolution, if we have to calculate, we have to consider 2000 clock cycles because that is the highest. Did you get it, Niranjan?
Yes, sir.
Okay, so that is why we are using 2000, not 190. Okay, so do not get confused between them. If you use 190, you are gonna get 21 millivolt, and if you use 2000 clock cycles, you will get 2 millivolt. So if you are anyhow, in any case, if you are going to get confused, just compare both of them with different clock pulses and observe which one has the lowest value. So that would be the resolution of the circuit. Okay, so that's another trick if you are going to get confused. Is that
Okay.
fine? Okay, cool.
Okay.
So moving on. So one more conceptual question is there. Okay, that if this 5 kHz, if this 5 kHz clock slows down by 8% due to aging. Okay, with time, let us assume that clock pulses are going to slow down by 8%. Okay, so how much error is gonna introduced in the meter reading. Okay, so this is the statement. We have to identify how much error will be in the meter reading if the you know uh, reduction in the clock speed by 8%. Any idea? Did you get the question first? So its answer lies in the first part itself, where we saw the slope, right? Where we equated. So this is not nothing but clock frequency. Okay. So here you could see, right, both the clock frequency terms are getting cancelled out. So even it does change, clock frequency change, your response will not slow down. Okay. So that is what the purpose of this question, that in dual slope type ADC, output or measurement does not depend on the speed of the clock, right? Because from this equation, or rather, if you have this equation, let me copy it. Okay. So this is the sharp looping curve. If you equate, what will you do? You will have Vx, that is the input. Let us write in terms of input. V input. V input into how many clock cycles it took. So it took 2000 clock cycles into time of or frequency of that clock. So time of clock. So it took 2000 clock pulses to reach the peak value, right? That was the 4 volt in that case. And while it was grouping or disintegrating, it was VR into 190 clock pulses. Right? So on both the sides, you could see that clock time period is coming out and they will be cancelled out anyway. So your measurement of input voltage is not depending on the clock pulses or the frequency of the clock. So that is why error will be, how much will be the answer of this question? How much error will be in the circuit?
Zero.
Zero, exactly. So it will be zero. It will be 0%. So that is one advantage with this kind of ADC, right? Okay, so I hope you got the idea of dual slope ADC. Any doubt in this part? In dual slope ADC? Okay, 0%. Yeah, NS, it is 0%. So let us see the next problem on which is linear ramp type ADC. Great. So linear ramp type ADC has the peak value of ramp is equal to 5 volt. Okay. Counter has 10 bits. Okay. And is driven by clock frequency of 20 kilohertz. Okay. Now we have to find out the maximum value of input voltage that can be converted with this kind of ADC. Okay, so this is our problem statement. Now, so let us see some basics of linear ramp type. How does it work? So you will have this kind of input, okay, which is gonna increase with ramp, and this ramp will have the slope of volt per second. Okay, so you will have one counter, and for some time period, let us suppose this is the time period t1, and you make your counter stop at this instant of time. Okay, so whatever the value it will measure, that will be your input value. So if you know the slope and if you know the time, you could get the input voltage, right? So input will be how much? V input will be equal to t1 second, t1 second into the slope, into the ramp slope. So slope unit is volt per second, and this is also second. Second into volt per second, so it will give you in volt. Okay. So this T1 will be, most of the time known that after this much of clock pulse, like in this value. So after here, I don't think it is mentioned, but generally it will be mentioned that after this much of time, we are gonna reset our counters so that you will get this value, and that this ramp slope will be given. Okay, so peak value of ramp here we know 5 volt. Okay, and we have to know the time which is it gonna take, or if it is giving directly this peak value, so what do you know, what do you need? You just need the value of input. Okay, so whatever the peak value of input, like it can reach at the end of the counter, that is gonna be the maximum value this counter can measure. Okay, so it is giving you directly 5 volt of the, in this problem statement, it is provided directly the 5 volt is the peak value which it is gonna measure. Okay, let us suppose that this is the 5 volt. Let us suppose we are extending it. Okay, and after that, mm, after that our counter stops. Okay, this is some time. Let us suppose t2. So it is taking total time t1 plus t2 to reach the peak value of the ramp, that is 5 volt. So if you want to measure the value less than 5 volt, you have to stop your counter before this t1 plus t2. So you have to stop. Let us suppose if you have to measure the input value at this instant, so you are gonna have to stop your counter at this instant, and since you have the slope 5 volt, so ramp slope in this case will be 5 volt divided by t1 plus t2, isn't it? So that kind of slope you will be knowing, and you will be identifying the input voltage. Okay, so here in this part, how much will be the maximum value of input voltage can be measured or can be converted? So now can you interpret with such a background? Okay, so let me explain it another way. If I'm writing another statement in a linear ramp type is driven by zero point 0.5, which by the way, this what I'm going to explain that was explained in lecture. So that is zero point 0.5 megahertz of the clock is being driven to measure the voltage with the help of linear ramp type voltmeter. Okay. Now at the end of the measurement, counter completes 200 cycles. Okay. Now ramp rate is also given. That is 5 millivolt per millisecond. Okay. So how much will be the input voltage? So to calculate input voltage, since we have the ramp rate given, okay, so we could easily multiply with this ramp rate into time, right? Because this millivolt per millisecond and how much time is being taken by the 200 cycles that we will have to calculate. So the time taken by the 200 cycles will be 200 cycles into time period, right? Which will be 200 into divided by clock frequency, isn't it? Which will be equal to 200 divided by clock frequency is nothing but 500 kilohertz or zero point 0.5 megahertz, which is 500 kilohertz. So it will be mm, 0.4, 4,400 microsecond. Okay, it will be 400 microsecond or zero point 0.4 millisecond. So that much time this counter will take to measure this much of voltage. Okay, so now we have the total time where the counter has been stopped and we have this ramp rate. Okay, so we can now easily find out our requirement of input voltage, that is zero point 0.4 into ramp rate, 5 millivolt per millisecond. This is also 0.4 millisecond. Okay, so how much will be the input voltage? 2 millivolt, isn't it? So did you get this part? How are we measuring with the help of linear ramp type voltmeter? Any doubt in this part? Okay, great. So Niranjan, now you have to let me know the answer of this part. Maximum value of input voltage can be measured with this problem statement, with this much of data. So here ramp rate is not given in this problem. Ramp rate is not given, right? So that you do not need to calculate the time consumed by the counter or the meter. So you are directly given with the peak value of ramp. So beyond that, it won't calculate, right? So the peak value is 5 volt. So the maximum value also can be measured, which will be 5 volt, isn't it? Beyond 5 volt, this will not measure. This particular ramp ADC will not measure. But maximum value will be 5 volt. But how much we are going to measure or how much is the input voltage? If any unknown input voltage is available with us, that must be less than 5 volt. Okay, that could not be higher than 5 volt. Then we can easily measure with this kind of ADC. right? So that is why maximum value is important. Otherwise, if you connect larger than the maximum voltage as an input, you are going to get wrong, or your circuit might get damaged as well. So that is why this is required. Okay, so maximum value of input voltage can be converted or measured will be 5 volt. Okay, do you agree? Do you guys agree with this? So, in any doubt on that maximum value of input voltage, how much will be measured with this kind of circuit? Okay, great. So let us move on. So now we have to find out the resolution of this circuit. So please find out, or please let me know how much will be the resolution of this linear ramp type voltmeter. How to calculate? So see, it's very simple because this counter will be having some, bits, number of bits as input, and it will have output. So basically, how this counter will act, since this counter has 10 bits. So there is a direct formula, which is resolution is nothing but peak value or that much of the value divided by 2 raised to power number of bits, that is 2 raised to power 10. Okay, since it has 10 bits, so it will have some value. So what does it mean? That to reach the 5 volt, since it is a linear ramp type, 5 volt to 0 volt, if it has 10 bits, which means 2 raised to power 10 steps it will take to reach till the 5 volt. So that's what the resolution mean in this, or for matter any question. So resolution or answer for this is 5 raised to power 2, 5 divided by 2 raised to power 10. So which will be 4.88 millivolt. So for that much of voltage, this circuit could detect. Okay, and that could provide the output corresponding to this kind of input. So if your input is going to experience the change of this much of voltage, 4.88 millivolt, it is going to provide you change in the output. If the input, if the change in the input is less than 4.88 millivolt, there will be no change in the output. Okay, so that is the part of resolution. Let's suppose we have resolution, we are given with the resolution. Here we calculated resolution, right? That much is the resolution of the circuit. Other way around, let's suppose we are given as the resolution of 10 millivolt, okay? And we have again 10 bit counter. So what will be the maximum value it can measure? Can we do other way around? We know that there are 10 bit of counter and we have been given with the resolution value. Can we calculate the range or the maximum value of the measurement? So that will be the maximum 10 millivolt, right, into 2 raised to power 10 bits, right? So that will be 1024. Uh, 102,
10.24.
yeah, 10.24, 10.24 volt, exactly. So 10.24 volt will be the range of this. So I think you got the idea behind this kind of linear ramp ADC, right? How does this measure and what are the roles of the bits? So if you increase the number of bits, you are going to have more ranges, as you know, but they will also occupy memory, so that you have to take care that how much the memory you want to spare. So that is the case. So any doubt regarding linear ramp type ADC? So it is just like, comparing each value in each resolution. Like if you have the resolution of 10 millivolt, right? And if you keep putting 10 millivolt, 10 millivolt, 10 millivolts, how many times? 1024 times. So then you are going to get your value or get your input value. No. Oh, regarding what, Niranjan? No. Okay, no doubt. Okay. I thought that. Uh, anyway, great. Let us say this ADC, like by last approach, we will see that can we get this. So if let us this time let us see the frequency is given as 1 megahertz. Okay, and this time you have to let me know. I want to use my pen, and input voltage is 5 volt. Okay, so how long do we need to measure this voltage? So time required to measure this voltage, and consider any resolution, because resolution will be required. So how much resolution do you want to have in this? So let me know the resolution, any value if you choose. How much should be the resolution? Any random value, any arbitrary value, you just let me know. And then you calculate how much time will be required to measure this much of voltage, which is 5 volt. Shall we take 5 millivolt if 5 volt is the input, like 1000 times? So resolution as 5 millivolt. Now please let me know the value of time required to measure the 5 volt. Then we are done with this topic. why I have proposed this problem, because we are gonna generalize, right? That relationship between time consumption and number of bits, how many number of bits are required. So it's simple, right? Resolution is 5 millivolt and input is 5 volt. So there will be 1000 clock cycles will be required, isn't it? Simple. Input divided by resolution, because that much times resolution have to work, or the clock has to be, you know, generated to provide us, right? So that will be 5 by 5 volt by 5 millivolt. So it will be 1000 clock cycles. Okay. If it is 1000 clock cycles and we have been given with the frequency, so time will be 1000 divided by frequency, which is 1 megahertz, which is 10 to the power 6 seconds. Sorry, 10 to the power 6 hertz, which will be 1 millisecond. So 1 millisecond will be required to measure this much of voltage. And this 1 millisecond would be equal to 2 raised to power n minus 1 cycles. Okay, so if consider we have 10 bits, right? If we have 10 bits, then it is gonna take 2 raised to power 10 minus 1 cycles. Okay, approximately, because you know it is not gonna give you at the end of the same cycle, so this will be approximately 1000 cycles. However, we know that it is 1023 cycles, but we are gonna take approximately, because 1000 will not come as a factor of 2 raised to power 10. Yeah, 1 millisecond. So if you take 2 raised to power 9 minus 1, so that is gonna give you the different value, 2 raised to power 9 minus 1. So that is way less, like 511. So the next closest value of n would be 10. So that is why we are calling it 2 raised to power n. So 2 raised to power n minus 1. If we have 10 bits, then it is going to take 2 raised to power 10 minus 1 cycle, which is a huge number of cycles, which is huge time, right? So we have to minimize, and that is when successive approximation type voltmeter came in the picture. We wanted to reduce this much of time, thousands clock cycles, or 1024, 1023 clock cycles. So we wanted to optimize this time. We wanted to, you know, make it faster, our measurement or our readings faster. We wanted to, you know, optimize it. We shifted towards our next ADC, which is successive approximation type voltmeter. So what does it do? So in conventional voltmeter, what happens that after every resolution, we verify that, yeah, is it matching, is it matching, is it matching, like 1 2 3 up to 2 raised to power n minus 1, right? Here in this essay, successive approximation voltmeter, what we do binary search. Okay, let us suppose we have the range of 0 to 5 volt. Okay, and we have to measure something, you know, 3.75. So first thing it will do, it will half the range. Okay, so the range will be 2.5. In on first clock, it will half. So it just follows the algorithm of binary search, which you might have studied in DSA. So it is 2.5. Now it will have to figure whether 3.75 is higher than 2.5 or less than 2.5. So it sees that it is higher than 2.5, right? So now what it will do? It will again do the binary and it will make division half among them. So this time what will be happening? The half of 5 and 2.5 is 3.75, right? So this will be 3.75, and if it sees that 3.75 is our requirement, then it will give you the output. So essentially, how many clock cycles it needed? Only 2 clock pulses will be required to measure that much of voltage, which would have been taken how much by the conventional or linear ramp type? It, it would have taken the number of cycles, that is 3.75 into 5 divided by how much would be the time. So it time of the clock pulse or frequency into frequency. 3.75 divided by 5 into frequency. So this much clock pulses would have been required. I'm not sure whether it is right. 5 into clock pulse. 3.75 into 5 into t clock, which will be equal to 3.75 into 5, because 5 would be the maximum value of ramp. Remember that 5 would be the maximum value, which means 5 into 1 by f clock. Okay, so that much exact time, if you compare both of the times, you will observe that the time taken by the SA successive approximation type will be way smaller. And by how much? So for that also, the exact expression is given, that since it is doing binary search, so we apply log 2 into 2 raised to power n minus 1 also, which would be equal to log of 2 raised to power n, which will be how much? N clock cycles. So in linear ramp type, it, it were taking 2 raised to power n clock cycles. It has been reduced to n clock cycles in successive approximations. So it is doing nothing, bigger task. It is just approximating with the help of binary search algorithm, right? So did you get the idea behind the successive approximation voltmeter? Any doubt in this?
ये लास्ट वाला कॉन्सेप्ट थोड़ा सा रिपीट कीजिए।
कौन वाला, ये log 2 वाला या ये वाला?
यस सर।
ओके,
हाँ यहीं
सो
से सर।
यहीं से ओके। तो यहाँ पे क्या हुआ कि सी, if we have been given with the range of any meter, right? So वो लीनियर रैम टाइप में क्या होता है, जीरो से रिजोल्यूशन, एक रिजोल्यूशन बढ़ता है 0.1 0.2 ऐसे ऐसे करके वो 5 तक जाता है, राइट? बट इसमें बाइनरी सर्च से क्या हुआ, वो 0 से 5 के बीच में बाइनरी मतलब बाय 2, सो हाफ किया 2.5। नाउ ये देखेगा कि जितना मेजर करना है 3.75, वो 2.5 से बड़ा है कि छोटा है? तो देखा कि 2.5 से बड़ा है, राइट? तो 2.5 से बड़ा है, तो इतने स्टेप्स तो स्किप कर सकता है आराम से, तो आधा टाइम तो इधर बच गया, राइट? नाउ इट विल ओनली सर्च इन दिस रेंज, राइट? यहाँ पे भी वो we can optimize our time, right? So what we will do, 2.5 और 5 के बीच में एक और half किया, that will be 3.75, and 3.75 is exactly what we needed. And I took this example why, because 3.75 is the convenient. Let us suppose we have to measure 3.65. अभी वो क्या करेगा कि 3.75 और 5 के बीच से ज्यादा है या 3.75 से कम है. 2.5, if we have to measure 3.65, it will have to 2.55. This is 3.75 and this is 3.65 assume. Okay, so अभी क्या होगा कि 3.75 और 2.5 और 3.75 और 5 ये कंडीशन चेक करेगा whether 3.65 lies in the range of 2.5 or 3.75 or 3.65 lies in the range of 3.75 to 5. Okay, so कौन सा कंडीशन यहाँ पे ट्रू हो रहा है? Which condition will
First one.
be applied? First one. So first one ये select करेगा. अब क्या होगा? First one select हो गया, then again it will divide by 2. So 2.5 और 3.75 के बीच में कौन सा आएगा? That we will have to measure 2.5 plus 3.75 divided by 2. So अभी आ गया 3.125. So 3.125. So यहाँ पे ये रिप्लेस करेगा 2.5 को रिप्लेस करेगा 3.125 से. ओके, 3.125 और 3.75 के बीच में 3.65, राइट? तो नाउ 3.65 लाइज बिट. यहाँ तक आ रहा है? आर यू एबल टू गेट इट?
Yes, sir. Yes, sir.
ओके
Got it, sir.
ओके, 3.125 से 3.75, राइट? एक सेकेंड, एयरपोर्ट इंस्टॉल. ठीक है, सो फर्दर ये क्या करेगा कि further it will divide, it will again perform the binary algorithm, and again it will find the midway. So it is just like, numerical methods में एक पढ़ते थे ना, binary algorithm फर्स्ट वाला, ये वही हाफ हाफ करता रहेगा, जहां तक नहीं मिलेगा वहां तक जाएगा. So basically it will reduce all the efforts of calculating at each clock pulses with increment in each resolution. So वो 2 raised to power n से घट के n टाइम से करना पड़ रहा है. Now it has to perform n times only. So are you getting the idea behind it?
Yes, sir.
Okay, great. So that is why we concluded that it is gonna take n clock cycles to mention if we have n bits of ADC. Okay. So that is how it becomes faster than our RAM type and all. And the fastest one is which ADC? That is flash ADC. But वहां पे क्या होता है कि जितने number of bits चाहिए उतना comparator we have to use. So in flash ADC, it becomes expensive compared to all the ADCs, right? So that is one drawback. If you want very high performance, you have to integrate that much of comparators, the number of bits we are going to require, and it increases the cost significantly. So many times you might be seeing flash types storage or so they are kind of expensive, and the reason behind that is more electronic components will be required. Okay, so let us see any problem is there. Yeah, so coming back to the linear type only, we solved two problems, right? One we solved resolution was 4.88 millivolt. Okay, so this was our problem. Let me copy it. Yeah, so this was our problem. Resolution we calculated 4.88 volt. Okay, so if we know the resolution, right, the next thing is that we have to calculate the maximum time required for the conversion. So let me copy it. we have to find out the maximum time required for conversion. Required for a conversion. So how to calculate? So since we know the total time this type of ADC, which was nothing but, let me remind, linear ramp ADC. It had 10 bits. Okay. So the total time required would be how much? Total time would be required to compute or to measure the maximum voltage will be how much time? 10 bits. So how much time? कितना time लेगा? 10 bits है 2 raised to power 10, right? 2 raised to power 10 clock cycles. But it is asking in terms of seconds. So 2 raised to power 10 clock cycles into time period will be equal to 1 by f clock, which will be equal to how much? 20 kilohertz. If you calculate, it will be 51.2 millisecond. Okay, isn't it? भूल गए क्या निरंजन? Okay, yes, NS. Okay, so this much time it will take. Okay, so now we have all the information. Please let me know the ramp rate of this ADC. What will be the ramp rate? We just need to calculate the slope of this ramp ADC, isn't it? Logan, are you getting this? 97.65 volt per second. Okay, so it is nothing but 5 volt is the maximum and 51.2 millisecond. So volt per second, you are saying 97.65, 5 divided by. Okay, yes, exactly. That's correct. NS 97.65 volt per second. So that much will be the ramp rate of this ADC. Okay, so I hope you will be able to solve the problems based on this ADC. Okay. Now, since we discussed successive approximation type, so now I'm going to write some data related to this ADC, and please let me know how much time will be required to measure this input voltage. So successive approximation ADC. Okay, 20 bit ADC. Okay, clock frequency is equal to 4 kilohertz. Okay, now how much time will be required to convert an input voltage? Let us suppose any input voltage V in is gonna be measured with this a successive approximation type of ADC. How much time will be required? So let us go step by step. First, calculate how much cycles will be required for conversion. 20 cycles. Excellent. So 20 cycles will be required for 20 bits ADC, which will be equal to 20 into T clock, isn't it? Which will be equal to 20 divided by frequency is 4 kilohertz. So it will be 5 milliseconds. Is that correct, Niranjan? You got? Okay. So let me repeat it. Since successive approximation types ADC has 20 bit ADC, right? And just now I discussed that for n bit of successive approximation type ADC, we will be requiring n clock cycles, right? Why? Because it is doing binary search algorithm. So that is why from 2 raised to power n clock cycles, it has been reduced to n clock cycles. And which the concept which we discussed, I just used that for 20 bit ADC is mentioned here, right? So for that 20 bit ADC, 20. Okay, you got it. Okay, so that was about successive approximation register. Now, again, another question related to flash type ADC. We are given with 16-bit flash ADC. So how many comparators will be required? Okay. So before proceeding towards the answer, what happens in flash type ADC? Let us see. Okay. So flash type ADC is connected in some fashion where multiple resistances are connected with the comparator. Okay. So let me draw that. Let us suppose in we have the resolution voltage V resolution. Okay. We have 3 bit of ADC. Okay. Which means N is equal to 3. And so measurable voltage will be voltage range will be 2 raised to power 3 minus 1. Why? Because if it is a 3 bit, we can measure till 7, right? 111. So it will be 7. So range is how much? 7 V. So if we know the value of resolution with 3 bits of ADC, we can measure till 7 times of that resolution. Okay. So that is why if you want to measure the higher range of voltage with the help of flash type ADC, you will have to use higher number of bits. Why? Because the range is dependent on the number of bits. Okay. So you have to increase the number of bits, and to increase the number of bits, you have to increase the number of comparators. How? That we will see. Okay, so since we have 7 resolution, we are going to use 7 comparator. Why? The reason you will get to know at the end. Okay, plus minus. Like that, they will be connected. This is 5. So total 7 comparators are connected. 4, 3, 7. Yes, right. Similarly, 7 resistance will be there, or 8. That will be depending on the connection. So all of them will be connected to one digital circuit. So which kind of digital circuit will take 7 inputs and take 8 inputs and provide you 3 outputs? Are you able to recall from the digital electronics? So this one considers that MSB X7, X6, X5, X4, X3, X2, X1, 1, 2, 3, 4, 5, 6, and 1, 2, and 0, 8. Okay, 8 comparators will be required since we are going to start from the 0. Please let me know that which circuit are you going to use when you have to take 8 inputs and 3 outputs. X0. And as the output, you will have 3. Why 3? Because we have 3 bits only at output. So Y2, Y1, Y0. Okay. Now we have this comparator connected to one ladder of the resistances, which is connected in certain different fashions. Like here are this positive will be always connected to supply voltage. Okay, that will be unknown. Okay, and what will happen to negative voltage? So that comparator will provide you as a high value for what? In last to last lecture we discussed the concept of comparator. So the inverting terminal should have the higher value than the non-inverting. Then only it will provide you the higher value, isn't it? So all the non-inverting terminals connected with our supply. Okay. Now what will happen to the inverting terminal? The resistances will be connected in such a fashion that when any value or any comparator will provide you high. So let me draw first. So this one resistance is connected to Yes, okay, so this value is R. Similarly, another resistance will be connected to another. Have you heard about demux circuit, demultiplexers? 8 cross 3 demux. Okay, NS has heard, Niranjan hasn't heard. So if you go through the digital electronics concepts in combinational circuits, you will be studying this. So what happens with demux circuit is it take 8 inputs, okay, or rather how many is the at the input, like multiple inputs it can take, and it can provide output as a number of bits available. Now in that, if time permits at end or in any lectures in between, if time will be there, we can discuss this multiplexers and demultiplexers. So for time being, Niranjan, you just take it from me that in demultiplexer circuits, we will be having 8 inputs and 3 outputs. Okay. So 8 in terms of, how do you arrange a circuit, and why we'll be having in terms of number of bits. So since we have 3 bits, we are going to have this kind of output. The working and arrangement we are gonna see in some other lecture. Okay. So this all these registers will be connected with mm, yeah, V reference. Okay. So this V reference will be connected at this terminal. Okay. And this V difference value will be how much? Just now we saw that range reference will nothing but range. And range is how much? 2 raised to power n into V resolution. So reference will be okay. Now see how it will be work. So how much voltage will appear at this node? At this node, how much voltage will be appearing from this connection? How much voltage could appear? At inverting terminal, here, let's assume V naught. How much voltage will be appearing? And all these resistances are. So if you take division rule, okay, so it will be V reference into R divided by 8R, isn't it?
Yes, sir.
And since we, yeah, so since we, so we can write V reference as 2 raised to power 3 V resolution, which is 8 V resolution. Okay. And V naught will be V reference into R divided by 8R. Okay. And V reference is also 8 V resolution into R by 8R. So V naught will be how much? V resolution, isn't it? Did you get this
Mm,
part? Okay.
yes, sir.
V naught will be V resolution. Similarly, if you see at this node, how much will be there?
7 आर होगा सर नीचे में.
Yeah, but in terms of resolution, it will be 2 resolution. So if you go ladder by ladder, 3 resolution, 3V resolution, 4V resolution, 5V resolution. So that much, let me write it here. Here V1, V1, 2V resolution. Are you able to see this? I'm zooming it for you. Similarly,
Yes, sir.
V2 will be 2V, V3, 3V resolution. So on, V4, V5, and V7. Okay. So now what will happen if V naught is higher than V input, because this op amp has two terminals, inverting and non-inverting. So if positive terminals V input is less than this negative terminal, then what will happen? If V naught is higher than V in, or V in is higher than V naught, then what happen?
नेगेटिव है तो आएगा सर आपके में.
Yeah. Uh, यहाँ पे भी इन कनेक्टेड है, राइट? अगर पॉजिटिव वाला हाई है, अगर नेगेटिव से, तो आउटपुट हाई होगा, राइट? ये कंपैरेटर का पॉजिटिव टर्मिनल अगर हाई है नेगेटिव से, तो आउटपुट हाई होगा. सो V0 डैश, anyway, this node I am writing as V0 dash, okay, which is 0 volt. Why? Because connected to ground. So V in will anyway higher than 0, or if we don't know, let us consider that V V in is higher than V0 dash. At that condition, X0 will be 1. Do you agree? Niranjan?
Yes, yes,
Okay. Now, for this X1 to be 1, what should be condition here? V in should be higher than V0, isn't it? This voltage. Similarly, here V in should be higher than V1, and so on,
G1.
so on. And if all the conditions are matched, then all will be 1, and what will happen? 7 is also 1. So that is like that. V in is higher than V2, and so on. So how it is helping in measuring so much of voltage at the same time? Because if you are going to feed only one clock pulse, okay, so it all the comparators will be working simultaneously, and the first comparator will be checking whether it is higher than the V0 dash. The second will be checking whether it is higher than V0. So like that, and if it sees that input is higher than 7 times of V resolution, like here, if you see V in is higher than 7 V resolution, okay, then what will happen? That all the inputs will be on, and your output will be X7. X7 will also be 1, right? If V naught is, sorry, if V in is higher than 7 V resolution, then all comparators will be high. So at that time, your output will be, since X7 is also high, all the comparators are high, then output will be 111. So let me draw the truth table of this. Okay. Why I am saying if all the comparators are high, then output will be high. X7, X6, X5, X4, X3, X2, X1, X0. Okay. So these are our truth tables. Let us suppose all are 0. It means none of the comparators are on, right? It means input voltage, whatever you are going to connect to the one terminal, which is the um, input is connected to non-inverting terminal. So whatever the input voltage, which is lesser than all the levels, which means if you are going to connect negative voltage as input, what will happen? Negative voltage will be anywhere lesser than 0 volt. So all the outputs will be 0. Why I am writing here 0, 0, 0? Because 0 of, in terms of absolute in 3 bits, since we have 3 bits available. So how do you write 0 in 3 bits? 0, 0, 0. How do you write 1? 0, 0, 1. Like that, right? So that we are going to write. Now next time, what will happen that this was if V in is less than 0 volt. Now the second condition, if V in is higher than 0 volt but less than 1 volt, then which of the bit from x7 to x0 will be 1? X1 will be 1, right? Because first comparator will be on, since it is higher than the 0 volt. Are you getting? And rest all will be 0. And 1, how do we write 1 in truth table? 0, 0, 1. Okay. Now let us see if V in is higher than 5 volt but less than 6 volt. How do you represent? Which of them will be 1 and which of them will be 0? You have to let me know. If V in is higher than 5 volt, okay, which means if it was higher than 0, means first comparator was on. If it is higher than 5 volt, which means sixth comparator will be on, right? Till sixth comparator will be on. And sixth comparator means till 5, like 1, 2, 3, 4, 5, 6. Okay. And rest all will be 0. And since x till x5 it is on, so we can write as 1, 0, 1. How do you write 5 in binary or decimal
Yes.
system? 1, 0, 1. Exactly. Right. Now, if V in is higher than 7 volt and less than 8 volt, how do you write? You just let me know this decimal terms in terms of decimal. Y2, Y1, Y0. So if it is higher than 7, so we have to make 1 till 7 bits. Okay. And it is coming at x6. Okay. So how do we write x6? 1, 1, 0. Okay. So this last bit will be 0. Are you getting the idea behind it? एक बार फिर से समझाएं निरंजन.
Yes, sir.
Okay. So let us see if it is less than 0, which means none of the comparators will be on. Okay. Which means
Okay.
output should be 0. And 0 को कैसे लिखते हैं decimal system में? 0, 0, 0. So that is
Yes.
what I am doing here. Okay. Next time क्या करेंगे? भी इन let's suppose कि जो भी दे रहे हैं वो 0 से ज्यादा है 1 से कम है. It is higher than 0 and lesser than 1. Then in that case x0 will be 1. Okay. Why? Because the first comparator will give you the positive output. Okay. Why? Because this positive terminal V in is less than the 1 volt and greater than the 0 volt. And whatever the V naught level here is equal to V resolution or is equal to 1 volt. So in that case, only X0 will be on. Rest all comparators will provide output as a 0. Comparator will just compare all both the values. So our output will be in terms of decimal. So decimal में 1 कैसे लिखेंगे? 001.
Yes.
ठीक है? Similarly, if Vn is higher than 8, it should not be, but if it is higher than 8, then all the bits will be, all the comparators. So these are all comparators from X0 to X7. So all the comparators will be high, which means in terms of decimal system, 7 we can write. Okay. And our output will be 7 times V resolution. How much ever will be the resolution, that will be our output. Nice. Thanks. Any doubt? NS, Niranjan? Any final doubt regarding this flash ADC? Okay, great. So let us coming back to our question. Our question was right, this one. So we have flash ADC, 16 bit of flash ADC. Okay, how many number of comparators will be required?
15, sir.
15. 15 comparators will be required. So Niranjan is telling me 15. What about you, NS? NS is telling me 16. NS 15 by Niranjan. What about Logan? Are you there? So in last topic, Niranjan is typing something. You could speak as well, Niranjan, no problem. 16, right? No. See, here, how many bits were there? 3 bit, right? And how many comparators we used?
7,
We
sir.
used 8, 7. 7 and one extra also we used,
Yes, sir.
right? So we used 8 comparators. So that is how much? 2 raised to power 3.
8.
2 raised to power 3. So here we have 16 bits of flash ADC. So how many comparators will be required? Yes, 65535. Exactly. That is the number. That is 2 raised to power 16 minus 1 comparators will be required. That is why it is so much expensive. Okay. So in this, with ground also, with ground this much, this comparator is redundant, that you could use or you could not use, because 0 voltage will anyway, there is no need to connect a comparator there. So that is why 2 raised to power n minus 1. So here with 7 comparators also our work would have been done. Just for explanation purpose, I used the 8th comparator at the end, right? So 2 raised to power n minus 1 comparators will be required to measure with help of flash ADC. And with 1 clock pulse only, your output will be measured. So that is why it is the fastest, but it is the most expensive. Okay. Yeah, 65535. Let me calculate 2 to the power 16 minus 1. Yeah, 65535. Okay, you're welcome. Now, final, we have to arrange fastest to slowest. We have been given with three ADCs, successive approximation, okay, as one, flash, two, and last one is the ramp ADC. You have to arrange it as the fastest and fastest to slowest. So the fastest we saw flash, so 2 is the fastest. After that, which one will be the fastest? Second fastest. 213. 213. Exactly. So that is the order. So that was just given. Yeah, right. So this much will be required to solve the week 9 assignment. I hope you will be able to solve all the assignments. Okay. Any final question before leaving? I think we are done here. Any final questions on this topic? Okay, cool. Oh, NS, no problem. Yeah, it is fine. You were very well active in during the session. No problem. Thanks a lot for being active in the session. So that motivates me to carry on. Thank you. Thanks a lot for joining. So there is no issue in that. Thanks to everybody, Niranjan, NS, and Logan. I don't think Logan is active, but I hope Logan has also. Okay, yeah, Logan. Now you reply. Thanks a lot. So I hope you got the concepts from this session. So yeah, that's from my side. I understand internet problems are there, but at the end of the day, you should take away the concepts with you, and you are able to solve the problems. Okay, Niranjan, बन जाएगा सारे questions?
हो जाएगा सर.
Great, nice. Okay, so nice, Logan, everybody. Thank you, thanks a lot. Thank you very much. So, I think we can conclude the session here. Let's meet next week, same time, same day. Thank you. You are most welcome, NS. Thank you. Thanks a lot. Thanks. Thank you, Niranjan. Thanks a lot. Thank you, Logan. Good night. Good night, everybody. Have a nice night.
Thank you, sir. Thanks, sir.
Thank you. Thank you. Thank you. Good night. Good night. Good night, Logan. Good night. Good night, NS. Bye. Good night.